Walking me out. There we go. Much better. Oh well. We get to see my taskbar. It'll be fun. Okay. Additive manufacturing. Has anyone heard of 3D printing before? Yeah. Additive manufacturing is just 3D printing. Well, there's other versions of it, but that's the essence of what additive manufacturing is. It's going to revolutionize and is revolutionizing how we make things. Today I'm going to overview the technology, go a little bit back into the older machines that we used to have. Then we're going to talk about how it works, especially with the laser sintering or laser beam melting technology, which is actually a technology we have here on campus, though I bet you didn't know about it. And then talk about the general capabilities of the technology. The original technology was a 1956 patent by O.J. Munz. It's called photoglyph recording. It's a very simple device in which it took a picture and then it built it up layer by layer, similar to the modern 3D printer. And we move on and we have plastic 3D printing. Well, it can be used for fun devices such as this orange device in the corner here. It's mainly used from a practical perspective for rapid prototyping. Everyone knows what a prototype is, right? Yeah? Awesome. So what this is useful for is that way we can get our prototypes out quickly, for example, this faucet, and work with it and modify it from there. Another fun way plastic can be used from a 3D printing perspective in metal manufacturing is investment casting. Investment casting is when we create some sort of pattern, so a positive object that we want to create, that we make a mold from that object and then melt the pattern out and then cast into it. So in this case, 3D printing would be used to create that casting. Moving on to the actual laser beam melting technology, Cal Poly IME Department, Industrial and Manufacturing Engineering, just got a machine this year for this specific type of additive manufacturing device. The technology itself is fairly simple. The powder on the roller here is spread across the base layer of your build plate. Then the laser melts on the specific spots that you want to have melted on for that layer. Then this layer goes down, more powder is spread on, and the process repeats. Next, I'm going to show a simulation on what it looks like, and it's going to show a couple of layers, and it's going to speed it all up, and that way you can see the overall effect of what happens. Now, in terms of effects for this device, the key is that we can create a new internal feature that we wouldn't otherwise be able to create. For example, this faucet, as you can see, there is no center line going through, but a bunch of little lines of water that go up to form the main line. While it is theoretically possible to create this through normal methods, such as machining it out, it would be incredibly difficult to actually pull that off, and I wouldn't want to try to cast that. So that's why 3D printing is good for creating new and different features. Another good example of this is from an engine block. This particular foam casting comes from a design study in aluminum casting. It was an August 2004 case study done by the American Foundry Society. In this case, they had to create an investment casting out of foam, which involved 4 different sections to get the internal features for the cylinder block for this engine. Instead, with additive manufacturing, we just build it up from the bottom with this finished product right there. Another thing that's great about additive manufacturing is that the waste reduction that's involved with it. Up here in the corner, we have a bunch of chips held within a fixturing device for material removal. Material removal is like a sawing or a drilling process in which material is removed from a block. In that case, it's very wasteful because all these chips that are left behind have to be gathered up, recycled, melted back down, and then it goes over and over again. So there's a small fraction of metal that's never actually used for a product. Meanwhile, with additive manufacturing, we have this big old powder bed that just gets reused over and over again. So the excess powder just needs to be smoothed back out and we can use it again. Mass reduction is also possible in two different ways through additive manufacturing. As described by Acta Materialia, a September 2016 article on the additive manufacturing of metals, a lattice pattern can be created through this method. While it is theoretically possible to create the same pattern, you couldn't create it on this detail level and keep the same structural integrity. The nice thing about mass reduction is you can keep the power of the actual strength of the object the same while reducing the mass. Things like bicycles, landing gear, anything where you need a strong object with minimum weight, you can maximize that and maximize performance. Another way you could do this is through the integration of assemblies. Moving back to landing gear, the economics of additive manufacturing for end-usable metal parts. It was an article by Eleonora Atzeni and Alessandro Salmi, February 2012, talked about landing gear and how they integrated a multiple part assembly into one singular part. An example of this is up here, in which we have an air duct, and on the left is through traditional methods in which multiple parts are put together and then bolted together. On the right, they built it up as one part without the need for the extra bolts or flanges coming out to connect things, which makes it lighter for the same performance. Overall, there are a couple of limitations to the technology, as described by Additive Manufacturing and its Societal Impact, a literature review in October 2012 by the International Journal of Advanced Manufacturing Technology. There is a volume limit to what you can create. As you can see here, we have a build chamber where you actually build the part up. You can't make a part bigger than that volume because otherwise it wouldn't fit in the chamber and you wouldn't have powder to build it upon. So as long as your part is within the size of your volume, you're okay. But once you start trying to build large parts, you have to get a bigger machine, which at some point isn't possible. It's also expensive for large batches. Each part costs a set amount, whereas with normal methods, the more you create, the less it costs per part. So at a certain point, it becomes too expensive to use this method. Overall, it's a great new technology. I just wanted to give you guys a sense of what this was going on. That way, when you're looking in the future and buying things and who knows, even maybe designing something, this is a technology you can use.